So again, in case somebody is unaware, me, David, Robert, and Heather, and we went to this conference organized by Ben Davidson, Observing the Frontier 2019, and I was one of the speakers, so I gave this presentation there, which is about the electromagnetic structures. So in particular, like for example, at the previous two conferences in 2017 and 18, I was mostly talking about like the atmospheric processes, like the possible influence of geomagnetic field and electric field of Earth onto, the formations of cyclones, of tornadoes, that kind of stuff. But here I just wanted to kind of broaden the scope. And again, I was kind of overly optimistic about my possibilities here. That, I mean, initially I was afraid that I wouldn't have enough material, but in the end, I've had more than enough material. I didn't have enough time, to deliver this material. So that was a problem. So, for example, these 2 points became rather trimmed because of that. I just basically skipped through them because of the lack of time. But we'll talk about the scalability of plasma, about the microscopic phenomena, which is particle physics, essentially, like nuclear physics and so on. Then this extended gold scenario, I'll explain to you what gold scenario means later. It's basically about earthquakes. And then a couple of points about this interstellar asteroid Oumuamua, which are also, at least in my opinion, related to the whole topic of, electromagnetism and structures and things like that. And then there's a section about more or less what we talked about with Jim. It's really like a discussion of Jim's ideas, nothing else there. And in the end, in the last section, I've talked about cycles and alignments, which was the other thing that kind of fascinated me in the last couple of months. So the key idea of this whole presentation is, like, I've tried to, walk through all these scales and show that the electromagnetism might give rise to various structures on all these levels. Well, again, it's not a new idea, not in any respect, but I kind of wanted to bring more detail to it, I guess, more spice, So this was a motivational slide, sort of. So I just wanted to say here that really I'm perfectly aware that there are a lot of theories that might be called, like, mainstream science and so on, that have certain explanations for all of that stuff. But I wasn't really interested in that. I wanted to deliberately go outside the box, so to speak. So some things that I speak about in this presentation are almost like, again, kind of deliberately strange, I would say, like, again, outside the box, that kind of stuff. And I just like this picture. It's from this it's an illustration to this book of Nietzsche's. It was the very first book on philosophy that I read, and it kind of means a lot to me. I got it from my father, basically, but that's a kind of a separate issue. So again, speaking about scalability, there's this paper by Hannes Alfvén where he discusses this idea of triple jump, which means basically that he says that, well, if you look at the scale ladder in the universe, you might find that plasma on these various different scales, like from cosmological plasmas to, the plasmas of interstellar cloud size, let's say, to magnetospheric plasmas around planets and laboratory plasmas, you can see that they are separated by these jumps of 10 to the power of 9th in terms of spatial scale. So his point was that it might be the case that more or less the same laws manifest themselves on all these levels. So And obviously, you know, it was later kind of picked up by thunderbolts and Perrat and so on. So it's really one of the foundational ideas in this whole plasma cosmology thing. But I thought that, well, why do we stop here? You know, maybe we should add another jump. Now, obviously, when we're talking about cosmology, there's pretty much nowhere to go up above. So let's just make another jump downwards. And we'll see that if we take the same jump, we encounter the level of atoms. This is exactly 10 to the minus 10th meters. This is exactly the size of electron shell of a hydrogen atom, basically. So, and we know that atoms are governed by electromagnetism, right? So it kind of seems very logical step to me. Like, why do we only limit ourselves with, you know, this thing when we know that electromagnetism works even here, and it actually works even better, you know, at this level. But then again, why do we stop here? Maybe we should make another jump of the same size, where we encounter the scales of 10 to the minus 19th meters. But here I should make a comment that it's actually the scales that are that we cannot observe with our current technology. So it's basically the limit at the moment. So here I wrote that maybe it's the size of, you know, quarks and electrons, but it's not really known at the moment. Like the highest bound is I think like 10 to the minus 16th or 17th in terms of, you know, the possible size of quarks and electrons, although both of them are considered to be point particles at the moment. So kind of the particle physics, the quantum field theory, does not consider them as having any size. But we'll talk about that a little bit later. But here, approximately at 10 to the minus 15th, we have the sizes that correspond to atomic nuclei. And basically, in this presentation, I'm mostly speaking about this part, the particle physics. You can see it's the biggest section of this talk. And then when we're talking about Jim's ideas, it's basically about that. So let's talk about the first one. So this is a comic, you know, from this XKCD series. They make like funny pictures about science, basically. So it's only here like to show, I was kind of bored, you know, with usual pictures with 4 fundamental interactions. So I just wanted to make it a bit more amusing, at least a bit. So it basically says that we have gravity with this neat inverse square law. We have electromagnetism with the inverse square law, and also Maxwell's equations. But we also have these 2 freaky forces, you know, the strong nuclear and weak nuclear forces, which we don't really understand I mean, how to describe them and so on. They're really very complicated. And so the natural idea that we can have here is that maybe we don't even need that. Maybe it's, you know, the complications of those, it just is just a consequence of, you know, us, well, basically of the fact that maybe those forces aren't even there. Maybe it's some manifestation of electromagnetic force that we just describe incorrectly. So, and here I want to say thanks to Eidos for making me aware of these works. Like in the following few slides, I'll be mostly talking about this paper. But the problem with it is that it wasn't printed anywhere. So it's kind of, you know, I became aware of it again just through email. So I don't exactly have any reference to it, except maybe those 2 which the author himself proposed to me as alternatives. I actually have a story to tell about this paper because, well, I'm not sure if it's no, I think I said that for later, but I think we'll discuss that with Eidos later. Yeah. Okay, so this paper speaks, they propose, among other things,
promise, right?
Huh?
That's the promise, yeah?
Yeah, exactly, yeah. There is some, I should tell you, there is some shady stuff going on in here. I'm not exactly happy with something that I've found, but we'll talk about that later.
I'll be all ears. Yeah.
Okay. So among other things, this paper proposes such a structure of an electron, which is basically a torus in their view. So what they talk about is that the electron is like a small spherical charge that moves along this torus. Okay, and this is kind of a stationary electron if it's not going anywhere. Again, it supposedly behaves like that. And this motion around the torus is what they call Zitterbewegung. It's a German word which literally is translated as trembling motion, but I have no idea why, but I have some affinity towards the word flickering. I think it sounds more cool, you know. So I would propose to call it flickering motion, but that's only my opinion. But why is it a German word in the first place? It's because it was actually proposed by Erwin Schrödinger, one of the pioneers of quantum mechanics. So he analyzed basically Maxwell's equations and Dirac equation and things like that, and he came to the conclusion that something like that is possible, basically. But even today, it's still considered to be hypothetical, even though he proposed it like in the early 1930s. So it's like, I don't know, 80 years ago, basically, or even more. Okay, so what they're talking about in this paper is, again, that the electron might move around this torus, which is called the Zitterbewegung. But what is usually understood under the motion of an electron is it's the motion of the torus itself. So it's a sort of a, you know, if we go really far away from the electron and observe it on a large spatial scale, we wouldn't see that smaller scale motion. We would only see how this torus moves in space like a, I don't know, like almost like a solid body or something. So here are some of the length scales, but I don't think it's reasonable to talk about that at the moment. So some of the other interesting results that are proposed, interesting points that are proposed in this paper are, for example, the analysis of some of the scattering data. Like this was the experiment of determining what is called the proton structure function, this F2 thing. And I wouldn't exactly be able to explain to you, at least in any reasonable time frame, what it means, but basically what follows from that, or at least what seems to follow from that, is that, and that's by the way, basically we're bombarding protons here, protons with electrons, and we're trying to see what kind of internal structure the proton has from that. And it seems to follow that from these results, and again, those are pretty serious experiments, like made at really huge labs, that proton might consist of muons, because you can see that this function has a maximum at the at what corresponds to 1/9 of the mass of proton, which is almost exactly the mass of a muon. Now, in case you don't know what muon is, it's basically like a clone of an electron, but it's much more massive. It's 200 times more massive than the electron. But kind of mainstream particle physics considers them to be almost like identical particles. They're basically like muon is an electron of the next generation, so to speak. But the properties, except for mass, are almost identical. And the other interesting result is about muons themselves. So it's the same type of process, the bombardment of one particle with the other, and trying to determine the structure function. But here it is muons and not protons. And it seems like muons have electrons inside of them because, again, this peak corresponds to roughly 1/200th of the times of muon mass, which is, again, it's the mass of an electron. But to say to somebody in particle physics community that, you know, proton might have muons inside of it, it would be a complete blasphemy, because, I mean, protons supposedly consist of quarks and not muons, and so on. And to say that muon might have electrons inside of it is also a big, It's a very, yeah, it would hurt your reputation so much that you wouldn't recover from that probably. But maybe something is there, you know, there's some data to indicate that. So who knows? And some other interesting points that they make is that, for example, the spin of elementary particles, like, again, in case you don't know what it is, it's basically an angular momentum, which is supposed to be kind of internal to the particle. So particle might, let's say, rotate around some axis. Well, that's okay. But there is, and it would have an angular momentum because of that. But there is also, according to quantum mechanics, some internal angular momentum to this particle, almost like the particle is, you know, spinning itself. So that's why it was called spin initially. But then people figured out that it couldn't be the case because the speed with which the particle should rotate is just it should be immense, basically. So and it's kind of a mystery to this day, what is spin, where it comes from. So what people do is they just introduce it by hand, just postulating it, never figuring out what its nature is, and so on. So. And I'll actually touch on that subject a bit later with regards to whether particles actually have some size, because obviously if particles are dots, they cannot rotate internally. That's just a contradiction in mathematical terms. And there's another interesting idea that neutrinos, in this paper again that I mentioned before, that neutrinos might be pairs of magnetic monopoles and anti-monopoles. Now, again, a magnetic monopole is basically an analog of charge, electric charge, but it's kind of like magnetic charge. And this object is, to this moment, it's considered to be hypothetical. But these guys give a whole bunch of references to other works that indicate that that might be the case, that maybe neutrinos are some sort of, dipolar-like combinations of these, magnetic charges, basically. Then we have in quantum mechanics a principle, of Heisenberg's uncertainty. And again, I should say that it is, at the moment, it is introduced by hand. It's a postulate, basically. And nobody really knows where it comes from, but it seems to be true, And it boils down to the statement that there are pairs of observable quantities, of observable values, such as, for example, the momentum and coordinate of a particle, that you cannot measure with infinite precision simultaneously. So you would always have some well, I guess randomness or something like that. If you measure the coordinate with infinite precision, you would have an infinite uncertainty in measuring the momentum, and vice versa. So what I understand, what their point is in this paper, is that it might be related again to some internal structure of these particles. Like, for example, if we're talking about the electron is a torus, let's say, well, then again, you cannot measure its position even accurately because, well, it's kind of spread out in space, it's not a dot. So it's kind of an intuitive indication that maybe even the uncertainty principle in the first place might be a consequence of some sort of structuring of these particles. Then we have this Pauli's exclusion principle, which is, again, basically a postulate that states that two particles with spin of 1/2, which are called fermions, cannot have a same quantum state. So something should be different about their quantum state. And again, I believe that if particles actually have some internal structure, if they have some size and so on and so forth, it's only reasonable to expect that you cannot just squeeze them into one quantum state, because, well, the state that is already occupied by one particle, the other particle cannot just jump into it because, well, there's other particle in there already. So kind of makes sense in my opinion. So again, it again relates to the statement that maybe these particles have internal structure and have size. And also quantum wave function is at the moment, it's just like almost like an imaginary number that we use to calculate stuff, but maybe it's related to some sort of, internal oscillations of these particles. But that would require a much longer discussion, so I'll just leave it like that at the moment. So there was another paper that Eidos and this whole Alienar group made me aware of, and that is this paper. And I'm just bringing this thing up from there, and it just reinforces really the point I already made about this, possible toroidal structure of an electron. So here, what we can see is that what is usually understood again as the motion of an electron is this motion along the axis of the spiral, but there's also this Zitterbewegung happening around it. And these guys, what they've been doing is just analyzing Maxwell's equations, and they got that from there. Well, then again, the question might arise, well, Maxwell's equations have been around for a while, so why didn't people notice that before, right? But it turns out that people actually noticed that. But what people started doing at some point is like artificially just killing some of the terms in Maxwell's equations that would correspond to that kind of motion. Because, well, the argumentation is that they're not physical, They're there, but they don't mean anything. So let's just get rid of them. So people introduce, again, by hand, artificially, what is called the gauge fixing. Like, for example, so these are, again, these are just restrictions that we apply to Maxwell's equations in order to get rid of some parts of them, let's put it that way. For example, we have Lorentz gauge, a pretty popular one, or Coulomb gauge, and there are a whole bunch of others. So my question here is, like, is it justified? Maybe we shouldn't do that, Maybe if the equations show us that something is possible, maybe it is. And I believe that that's a completely valid question. Well, although, I don't know, maybe it's debatable. And this is my comment to that paper. In particular, in particle physics, there's this big thing called local gauge invariance principle. And it's kind of complicated to explain what it is in detail, but just using very broad strokes, I can say that this whole gauge thing is about some sort of imaginary rotations of imaginary objects in imaginary space, But then from that, people use, really complicated math to generate from these, transformations, like purely mathematical constructs. They generate the real particles, the real fields that are observed. And the kind of the problem is that nobody really knows how it works, and nobody even, bothers asking such question, like why is it working in the first place? Such a complicated formalism, but it's really like the main pillar of particle physics right now, and so somehow nobody cares about, the fundamentals of it essentially. So my idea here is that maybe all these complicated transformations only work because there is some real structure, of real objects in real space. So maybe it's just a very weird way of describing the real, reconfigurations of particles, some sort of, I don't know, rotation, oscillation, whatever, something like that. And it might be productive, to look into that in more detail, like how exactly it might work, why does it work, and so on. So I kind of plan to do that in the near future. And here are some of the other interesting points that they make. You can pretty much ignore that. So what's most interesting to me is that they found that you can generate the masses of certain particles from the masses of other particles just by using these very simple rules. Like here, this 1 + 3n times mass of pi meson. and here 1 plus 8n times mass of muon, where n is basically just a natural number. So I was immediately struck by it because that's exactly what they call the SU3 group in this whole group theory. Again, this is just a bunch of imaginary transformations of imaginary objects, but the numbers are the same. The SU3 group has 3 basis vectors and 8 group generators, and you can see it really clearly here. And I think that it's another indication that I'm on the right track here. I mean, with regards to what I talked about here. So again, maybe something would follow from that. But again, I've already mentioned that the possible structure of proton might involve muons and so on. But of course, in mainstream particle physics community, the proton is supposed to be an aggregate of these so-called quarks, right? So, so supposedly in a proton there are 3 what they call the valence quarks, that form sort of a backbone of the particle, but at the same time a bunch of so-called C quarks constantly appear and disappear inside of a proton, and not only proton but any other particle like that, like for example neutron and so on. But the problem is with quarks is that this quark model, it might it gives you a correct description of mutual transformations of particles, like what proton can turn into basically when it undergoes some high energy process and so on. But the problem is that you cannot take a quark out of it, and that's what is known as confinement of quarks. It's basically the statement that quarks are free particles only inside of the proton, or again in any other hadron and so on. But if you try to take them out of that, say by giving it some energy basically during some process, it doesn't manifest as a free quark, but rather it manifests as other hadrons. So supposedly what's going on, the quark just takes up particles from vacuum, like additional quarks, and forms other hadrons, and you never see a free quark. And the point that these guys are making, and again, by the way, I made there a comment that my PhD thesis is all about the physics of quarks. So kind of the point I'm making right now is directly contradicting my own, academic research. So, but tough luck, basically, yeah. So what they're talking about in that paper is that maybe it's the consequence of quarks not being real particles. Like maybe they are just quasi-particles, some sort of excitations, particle-like excitations that can exist only inside of a proton, or again, neutron, pi meson, you name it. In that case, it wouldn't be surprising that you cannot take them away from that because, again, well, they are not real particles. And the funny thing is that in condensed matter physics, like, solid state physics, semiconductor, that kind of stuff, we know of many of such quasi-particles, like, for example, phonons, that correspond to some excitations of the lattice, or some other particles like that, and so on. So it has been known that even particles with fractional electric charge might exist there, which is, by the way, the case for quarks. They supposedly have the charge of, which is 1/3 of the charge of the electron. So it's a really strong point in my opinion. And yeah.
I hate to interrupt you on a beautiful roll here, but you said I can ask a question if it's on the topic, right? If you want to put it in the end, that's cool too. But could I make the suggestion that, how can I say that? You're pointing to that right now, calling the quarks 1/3 of the electron charge, I believe?
Yeah, their charge is supposedly 1/3, yeah.
Yeah. So if I look through the structured atom model glasses, I can see that every nucleon, regardless of it's a proton or a neutron, right? Every nucleon that is added to the nucleus in a structural model always, at least on average, 99 point something %, makes free connections but uses for those free connections 1 electron charge, if you will. So one connection, free of those, is 1/3 of an electron charge. To me, and this is, well, not maybe a suggestion, but the remark I would like to make, and I hope you can treat it as a question there, Eugene. Let's put it this way, do you see a connection there? Because I do see a connection, or at least a huge coincidence, if you will. So in the structure that you're alluding to, free connections divided over 1 electron charge, it sounds suspiciously much what you're talking about. Thank you sorry for the interruption.
No, it was on point, and I actually want to thank you because I wasn't aware of that, and that's potentially very important, I think. So thank you.
Okay, well, we can dive into that maybe later on into more detail. I'll let you go now for now.
Yeah, but that's very cool. I mean, yeah, okay. Thank you. All right, so okay, so here you can see the charge distributions in neutron and proton. And again, what they do here is, I mean, to acquire this data in the first place, is they bombard these particles with electrons. And from that, they infer, you know, how these charge distributions look like. And you can see that in the neutron, there's sort of a positively charged internal part and negatively charged external part, whereas, you know, proton is just all positive. But it's really obvious from here that they're not point-like particles, right? That they certainly have some spatial dimension to them and so on. And neutron even has some charge separation, if you like, inside of it. But again, at the moment, it is supposed to be a consequence of this type of structure, that there are quarks inside of it, inside of these both that give you these distributions. But maybe it's not the case. Maybe something else is going on there. And here are a couple of other papers that I would like to mention. Like this paper, it tries to get rid of the strong nuclear force by just supposing that neutrons are getting polarized by protons. So whenever a proton approaches neutron, the neutron would kind of reconfigure itself in such a way that its negatively charged part would be closer to the proton. Just, you know, just what happens in electrostatics, you know, the induction. And that way, it would actually have an attractive force. So these particles would be attracted just through simple electrostatics without any necessity to introduce any other forces. And kind of the most important thing about that paper was probably that this guy, well, at least he claimed to be able, I haven't, you know, checked his calculations, but they, on the surface at least, they look pretty good. So he claimed that he was able to predict binding energies, to calculate binding energies of isotopes of hydrogen and of helium also. And that's pretty amazing. I mean, the accuracy that he got wasn't very spectacular. It was like the error was maybe 30% or so. But the thing is that with strong nuclear force, you cannot do even that. Like you have to, again, kind of tweak your model a lot, introduce a lot of ad hoc, you know, phenomenological models to even estimate at least, you know, approximately these binding energies. Whereas this guy haven't done anything like that. He just, you know, took this really simple electrostatic polarization model and got a reasonable result from that. And that's quite amazing. So again, it might be a hint that, you know, maybe electromagnetism is the key force even on nuclear scale. And then there is another paper from the same guy. It deals with the scattering of alpha particles, like, you know, the Rutherford experiment, quite famous one. So you have alpha particles infalling onto the gold foils. Well, it doesn't really matter what is here, but I mean, they took gold foils initially because they could be made really thin, and that's what they wanted to, you know, to be able to observe a particle that only undergone one collision, sort of. Because if it would be very thick, you would expect a lot of collisions inside of it. So that's not what they wanted. But anyway, it's a really super standard experiment that had been done multiple times, especially in the beginning of the 20th century when people were developing that stuff. So you place a detector somewhere at some angle and you observe these scattered particles, okay? And it has been known for some time. I mean, supposedly what happens the more energy this infalling particle has, the closer it can get to the nucleus of gold, let's say in this example, because, well, otherwise it would be repulsed because it's positively charged and the nucleus is positively charged. So there's a Coulomb repulsion in between them. So you have to have a lot of energy to get closer to the nucleus, until you're getting deviated. And it has been known that if you observe that this system from a fixed angle, I think it's like 60 degrees here or something, then as you increase the energy of infalling particle, you have kind of initially a nice Coulomb repulsion, but then your flux just plummets. So something else is starting to be involved at the closer distances to the nucleus. And naturally, people thought that it was the strong nuclear force that was, very short range force, so that it was becoming important only in this higher energy area. But what this guy did in this paper is he said that, well, let's just take magnetic repulsion into account. And as far as I understand, he was able to reproduce the same result. So basically, you have just electrostatic repulsion, or at least mostly, in lower energy area. And then you have just a magnetic repulsion at shorter distances, because obviously, I mean, magnetism falls quicker with distance than the electricity. So it becomes important only at shorter distances. And that's also...
Is that discontinuity like at a predictable ratio, speak, where you have 10 to the 2, I guess. Does that happen consistently at that?
Do you mean the
little elbow between the corrected Coulomb right there? Yeah.
Do you mean what slope is, or do you mean where it happens, like on x-axis?
No, between the corrected Coulomb curve and the Poisson magnetic curve, that point of intersection is that experimentally at a solid position.
This point?
Yep. Mm-hmm.
Yeah, and it's, by the way, what's interesting is that it's around the energy of, the binding energy of alpha particle itself. So maybe what's happening is that here alpha particles already have enough energy to basically, explode, so to speak. So they might be represented as bunches of protons and neutrons rather than a single particle. So maybe that's what, causes...
Eugene?
Huh? Yeah.
This represents alpha particles onto a gold foil, right?
Yeah, it's a Rutherford experiment.
Right. You see a distinction, as you point out, between the electrostatic repulsion and the magnetic repulsion.
Yeah.
My question is, do you see the same curvature with free neutrons, free neutron bombardment? Would you see the same effect there?
Well, that's a good question. I mean, if you just what is 3 neutrons? Do you mean helium with 3 neutrons?
No. A free neutron, so a neutron bombardment.
Free neutron.
Yeah, neutron bombardment. Because
I don't know.
Neutron would have a very different electrostatic field or electromagnetic field, or charge-wise, it's much smaller, I believe, than a free proton, for example. I'm curious if a neutron would show the same curvature, the same effect. That was my question.
Yeah, well, unfortunately, I don't know the answer. So,
we'll put it on the list.
Okay. Well, that's a good question. I mean, how the Rutherford experiment works with neutrons. Yeah, that's a good question. I mean, obviously, you wouldn't have a Coulomb curve because it's not just, plus charge, it's something else. Most likely something more or less dipolar, or maybe a bit more complex. But yeah, well, that's a good question, definitely.
We deferred your flow a little bit, sorry there.
No, it's okay. That's exactly what I want. No, I mean, Eidos' comments are just spot on. So, you know, they're really, really good questions. Okay, so, and again, so just to sum up what I've talked about here. So maybe we don't need, you know, strong nuclear force. That's basically the point. Maybe the electromagnetism would be enough to explain all of that. And there's another paper that, again, Eido made me aware of, and Jan Emming also. So in particular, there are a couple of interesting things kind of shown there. For example, this idea that the nucleus might be almost like a solid body, you know, it may have some lattice and so on. Now, obviously, Eidos' model also has something like that. I mean, the idea is somewhat similar, but I mentioned Eidos' model later here. So that's one interesting idea. But another thing that I wanted to talk about with regards to this paper is that the author goes a sort of a different direction. So he considers nucleons as being coils with a current, right? And he tries to describe the nuclear force as being the consequence of magnetic attraction of these coils with current. And now there has been a lot of discussions about this paper recently, but I actually should say that I don't like what this guy is doing. But why am I showing it is just to, well, to show basically that even under this huge overarching idea that maybe it's the electromagnetism, you still have different possibilities and different people explore them. You know, like maybe it's electrostatics, maybe it's that kind of magnetic attraction and so on. And I think it's very cool that people have different opinions because it creates a sort of a competition in this area, which is very productive as far as I can tell, at least. So, yeah. Right, so this is another indication, at least in my opinion, that there might be some structure to the nucleus, all right? So you can see such graphs in many different papers. This is just one example. So here you can see the same type of experiment, the same scattering of alpha particles. In this case, it's on the nuclei of calcium. But here you vary not the energy, but the angle at which you observe them, all right? So this angle between the detector, basically the scattering angle. So you place the detector here or here or here or here and so on, and you measure the flux at the same energy, and you get this weird distribution of fluxes. So in my opinion, the fact that you have these kind of peaks and troughs at different angles, it's a kind of a secondary indication that there might be some internal structure to the nucleus. Like almost as if there was some, you know, shells of different charge signs or something like that, so that, you know, under some angles the particles would bunch up because of that. Under some angles there would be almost no particles present and so on. But I should note that usually, like in mainstream physics, it is explained through quantum thing, like interference of partial waves and things like that. But maybe it has some, you know, actual physical foundation. That's kind of my point here. Okay, so this is another interesting paper, and we've discussed this a little bit in the chat, I think. So again, it's the same process. And by the way, yeah, okay, I'll make that comment later. So this is the same process of scattering of alpha particles on some nuclei. I'm not sure which ones, but that doesn't really matter. So what this guy is trying to do in this paper is he takes all these measurements of fluxes at different angles and so on and so forth, and he tries to reconstruct a potential. So what is potential is essentially the energy of interaction of this alpha particle and the nucleus, which is bombarded by it, with respect to distance in between them. So that gives you a kind of a hint on the internal composition of the nucleus, at least potentially. And the funny thing is that he mostly gets this Coulomb curve, 1/r, or yeah, if we're talking about potential, it's 1/r. But he also notices that there is, some oscillatory thing kind of crawling on top of this Coulomb curve. And he just takes, the full result that he gets and subtracts the kind of the pure Coulomb curve from it in order to, isolate this oscillatory term. And what he gets is this thing, this what I call correction here. And it's very peculiar looking, right? So it has like, well, okay, I'll just let the guy himself speak. So what he's writing there in this paper is that it seems like this structure is equivalent to a series of shells of alternating charge. So you have negative charge here, then you have a layer of positive charge, then again, the layer of negative charge, the layer of positive charge, and so on. And that's all is happening inside of the nucleus. But then again, it's only kind of a small correction. Not very small, it's maybe like 10% of the whole curve in magnitude, but it's there, and we can measure that. Now, kind of the question is, and I've actually searched for that a lot. I've been searching for more modern studies on that subject, because you can see it's 1931. It's actually even before people proposed the existence of neutrons, which was 1932. So it was really, the dawn of this whole nuclear physics thing. So I've been searching a lot to find more modern studies on that question, but I haven't found any. And I think what's going on is that people kind of just disregard that. They've said, like, for example, you could have seen on some of the previous charts that they talk about corrected Coulomb curve now. So my idea, my suspicion about it is that they just kind of sweep it under the rug and say, okay, well, here we have more or less Coulomb. Yes, there's a slight correction to it, but we'll just say that it's mostly Coulomb and just forget about it. But maybe it's actually the important part. I mean, it clearly shows that there is some internal structure to the nucleus. It's not just, the nucleus is not just all positive charge, there is some fine structure, some charge separation inside of it. So that's kind of the point I was trying to make here. Okay. Yeah, so this is, well, I just wanted, to have fun. So it's a major pain, in case you're not aware.
I hate when that happens.
Yeah, so kind of the idea is, and again, it kind of relates to Eidos' model and Eidos' question, that maybe neutrons actually don't exist inside the nucleus. That's kind of the point. And returning to this very first, now, here I should make a kind of a correction that what is a free neutron is kind of a different subject. Like, we don't, I mean, it's not really clear at the moment, but there is a pretty strong indication that neutrons inside of the nucleus might not exist. That's the point here. So again, I'm returning to this very first paper that I've mentioned, where they propose such a structure, for example, for deuteron, the nucleus of hydrogen-2, where you have two protons and an inner electron in between them. So usually what is considered to be a deuteron is just one proton and one neutron, which is in this case represented by a pair of proton and electron. So this is kind of the idea I'm talking about here. And there I mentioned also the Eidos model. Now, I'm not sure I need to talk about that much, but I basically said that, I guess I could say you, because you're present on this call. You were a speaker at the EU 2017, you have this website, and kind of the main idea of your model is that the nucleus has some structure to it, like some actual, almost like a solid body type of ordering inside of it. and that again, the interaction is mostly governed by some sort of electric forces, let's put it that way. So neutrons aren't there, but rather what you have inside of the nucleus are a bunch of protons and inner electrons in between them, which again kind of keeps this whole structure together, right? Well, and it's a pretty interesting model because it's really easy to understand, and it's very visual, right? So you can look at this structure and so on, and pretty detailed, and it already gave some really interesting and important hints. Like, for example, as far as I understand, you're able to calculate the binding energies of nuclei. To evaluate the stability, just basically by taking the sum of these, individual connections of protons with electrons in between of them, and you are able to evaluate the stability of the nuclei just by looking at, how warped the structure of the nucleus is. So that's also an interesting thing, and maybe, and we've discussed this several times, there are some connections to chemistry, like maybe even the external electrons that allow chemical bonding to happen. Even their distribution in space is somehow depends on the structure of the nucleus in the first place. So it's also a very interesting thing. Again, we've talked about that a couple of times, that maybe there are, according to this model, as far as I understand, there should exist basically new elements, like right in the middle of the periodic table, but they would be probably confused to the existing elements, and it's kind of a question that we're working on now, is to maybe there is actually some difference to them still. Like maybe some effects are known that might be explained with the help of this model in that regard. And obviously, like the holy grail of this whole thing is to make possible the low energy nuclear reactions. And I believe that actually Eidos' model is a very promising vehicle, like a very promising step in this direction. Like, but that's obviously, we're kind of far from that yet, but I mean, who knows? Okay, so this is the idea that I've had, and I've actually, I think I wrote it in the chat someday, but I was just kind of struck by this analogy of magnetic reconnection and some of the processes in particle physics. So it's just sort of a mainstream description of reconnection, and at the moment, for the sake of this argument, I don't really care if it's true or not. I'll just use this description. So suppose we have this kind of flow of particles in with this sort of magnetic field structure. So when they connect in this point, you have this X-shaped magnetic field structure that can later snap in this point and become organized like that. So the kind of the topology of the field completely restructurizes itself, so to speak. And you have on the contrary, the flow of ions in these opposite directions that are kind of associated with these new configurations of fields. And what struck me about it is that that's almost exactly what we see in some of the strong interaction processes. Like, for example, what you can see on like Large Hadron Collider and other devices like that. Like, you can have protons with really a lot of energy kind of combining, interacting in a point, and then suddenly you observe these so-called hadronic jets, the jets of other hadrons from that process going in the opposite direction. So kind of my idea, and it's not really, you know, detailed at the moment. It's just an intuition, basically, is that maybe it is related to this magnetic reconnection process. So therefore, maybe it is electromagnetic in the first place, you know. That was my point here. So again, maybe we don't need strong nuclear force. That's what I'm saying. It's just kind of out of curiosity. I found that reconnection also happens in DNA. Like DNA strands might also change their topology in such a burstful manner, so to speak, you know. And it's pretty interesting. So you might look up that paper if you like to learn more. Okay, so it's kind of more or less the end of this whole section. So here I want to ask and by the way, I'm kind of moving too slow. I'm not sure. It looks almost like I would
do it
need
in
2
sections.
hours.
Yeah, we could do it in sections if you want. Yeah. This could be section 1. It's great. It's great, but it's a lot, you know, of course.
Yeah, but I mean, I just, you know, I just have this feeling that I wasn't able to tell as much as I wanted during the talk at the conference. So
yeah,
I wanted to expand it a little bit.
Yeah. The role is awesome from this point of view, anyways.
Okay. Well, thank you. So here I'm returning, you know, to these issues with quantum spin, like Heisenberg uncertainty and things like that. So it's a very important philosophical question, in my opinion. Like, can an object without a structure, you know, without any size, have like any properties at all? Basically, can a mathematical dot have any physical properties? That's what I'm asking here. And I would say that this question cannot be solved like it's almost like an ideological question, if you like. So you can think that it can, and you can think that it can't, and it's just that it gives you different, you know, pictures of the world. And here I just mention Descartes with his, you know, ideas that we've actually talked about it yesterday a little bit, that, you know, Descartes he basically separated the whole world into, you know, the physical world, which he called res extensa, which means basically the stuff that is extended in spatial terms, right? The stuff that has size. That's the objects of the physical world. But he also said that there's this res cogitans, which means like conscious stuff, basically, which is a soul, and he considered it to be to not have a spatial extension, you know. So according to Descartes, in a human, you have both this part, which is his body, and this part, which is soul, and it's kind of attached to the body, but it's not equal to it. So it's kind of an important moment in Western philosophy where this divide happened, and so on. So with regards to this question, I believe one can say that there are two ways of answering it. There's a sort of a Newtonian approach where you say that, okay, well, physical bodies are just, you know, solid spheres or something like that, which are surrounded by emptiness, by vacuum. And just by looking at how these solid spheres interact with each other, you can derive from that the properties of larger scale objects and so on. And obviously, if you have a solid sphere, like impenetrable, you know, something like with some deep ontology and so on, you can shrink it into a dot that wouldn't have any size, because if the sphere was impenetrable in the first place, it was almost like a discontinuity in space in the first place. So Newtonian view would say that, yes, probably an object without a size, a mathematical dot, might have any properties, like any properties you like. But there is a Cartesian view, I would say, which boils down to this fact that he only considered like objects that have some size to have any like properties, to be physical objects, basically. So in the eyes of, you know, this Cartesian approach, if you don't have any size, you're not a physical body. So why am I telling you all this? Is because, again, it's kind of to reinforce this position of mine that maybe all these particles that we're dealing with should have a size and should have a structure, because otherwise they wouldn't have any properties. We wouldn't even detect them, and so on and so forth. And in general, I would say that modern particle physics is much more in line with the Cartesian approach than Newtonian. There's also an interesting insights from Nietzsche, and that's kind of regarding this point, that Nietzsche considered an atom, the very idea of an atom, as something indivisible, you know, something, again, solid and impenetrable, as basically a mirror of this idea of a soul. And it kind of comes from here. Like, if you don't have this notion of a soul as something that cannot be divided, you wouldn't even have the concept of an atom later, because, I mean, why would there be any atoms? Well, okay, that's a, you know, that might be a long discussion. And the interesting thing is that even Karl Marx had the same idea in his PhD thesis, which is, it's really great. I mean, that some of the ideas there are really kind of mind-blowing. But I mean, I'm not exactly in favor of Karl Marx, you know, in terms of, you know, his economic and social theories. But that was before, you know, before he met Engels and was basically recruited by British intelligence, you know, wink, wink. So this is the work that deserves attention. He was just he was just a young aspiring philosopher back then. Without it's just you were waiting for that. Yeah,
I like the outfit.
You got some dark corners.
Newton's outfit, I like.
Yeah, well, it's a really kind of a famous meme right now in the Russian internet, especially. This movie, but I wouldn't name it. So if you're not aware where it comes from, it's perfectly okay. But that's Descartes and Newton, but if you have recognized that. So a conclusion to this section is that I believe there's a very captivating possibility to make sense of these, you know, epicycles, this overcomplication of nuclear theory. And I hope I was able to show you that that is the case with just using, you know, very simple electromagnetic centered approach to all these issues. And it seems to be a lot of evidence for elementary particles having a structure, internal structure, and having some size and so on. And here I've also mentioned this Bostic's research. And on this podcast, we've mentioned him a lot. Well, maybe not a lot, but sometimes. But I should note that I'm not really well aware of his research, so I cannot, you know, comment on that much. It's just that I've heard that he was considering elementary particles as, you know, plasmons. So some sort of metastable or quasi-stable configurations of plasma. But again, I cannot comment on that much. Well, that's pretty much it with regards to this section. So let's talk about this extended goal scenario. So it's the research that we've done with Heather about earthquakes. We've done a lot of kind of strange research, let's put it that way. It wasn't really fruitful, but some of the interesting thing has surfaced from that. Like, for example, I've noticed that strong earthquakes like magnitude 8 and higher only occur in between roughly like 61, 63 latitude. So there is a sort of like a belt where they might occur. And that's pretty interesting. In my opinion. So I thought that maybe there is some, you know, maybe it's important, maybe it relates to something. So at first I've noted that the angle between the Earth's spin axis and galactic north is 63 degrees. So that would mean that this belt where these strong earthquakes are happening, it actually consists of the points that kind of pass through the galactic plane as the Earth rotates. So here's the galactic plane, properly oriented with respect to the Earth's spin axis. And as the Earth rotates, it kind of sweeps out exactly this belt in between 63 north and 63 south, where these stronger earthquakes occur. So maybe there is a relation here, I thought. That it's just another angle. And that's not the proof of hollow Earth theory, by the way, at least, not yet. But then I thought, well, okay, well, how would galaxy influence that? Maybe something else should be involved. So I looked at Van Allen belts, and interesting thing is that they also are mostly prominent, again, roughly in the same latitudes, like from 63 to 63, or about so. So I thought that maybe, some sort of perturbations here that would be caused by, let's say, space weather, like solar wind and cosmic rays or whatever, might, kind of perturb the belts in such a way that they would cause some sort of induction or whatever in the crust, which would again produce earthquakes through some not really well understood mechanism. That's one possible idea. But then I've stumbled upon this paper by Bob Johnson, this first one. So what he does there, and then there was also a presentation that he gave recently on the same topic. So what he does there is he comments basically on that old paper by Thomas Gold from 1963. And okay, and he calls this the Gold scenario, what he describes there. And Gold was considering a huge, very powerful CMEs and their possible impact on Earth. So this is the picture from the Gold's paper. So you have this cloud of plasma falling on Earth, like really high energetic CME, like extremely strong, let's say. And there are these, as it encounters our ionosphere, there's this current going on in there. And so Gold said that, well, wait a minute, you have this pretty thin layer of atmosphere here. So what if these currents might actually break the atmosphere down and go right through the crust? That was his idea. And what Johnson did in his paper is he calculated how much energy would this thing have potentially. And he estimated that for a really extremely strong CMEs that might occur, I don't know, maybe once every 100,000 years or something like that, you can have enough energy to raise whole mountain ranges with just with these currents. They would cause
Eugene?
Yeah.
I need to applaud you here. I think you just pointed out for the first time a realistic scenario of how we can get the thunderbolts of the God creating our Earth geology through electricity, whatnot.
Yeah, exactly. So
absolutely fascinating.
Yeah, so this is, by the way, one of the ideas that Johnson right now promotes, and I think maybe you've heard of him, Rens van der Sluis.
Yep.
The guy who worked with Thunderbolt. Oh yeah, well he's from Holland also, right?
I met him in Phoenix, but
yeah, no, yeah, I think he lives in Korea or Canada or
South Korea, I believe. Yeah.
But he's like one of the most diligent researchers. So I'm really happy that I know him. As by the way, is Johnson. He's also quite amazing. So I think it's the scenario that they consider the most plausible at the moment, that all these plasma columns or whatever was really caused by something like that. So it wasn't a planetary encounter or something, but it was rather, well, some influence from the sun, like in the form of
regardless of that one, what you point out here is that you can get a huge electric discharge right?
Yes, exactly.
Capable,
Exactly.
as you mentioned, in energy of
Mhm.
raising a mountain range.
Yeah,
That's
and
good.
not only one discharge, it might occur everywhere, basically, like anywhere on the planet, and even simultaneously. Um, but
I could
that's
imagine a circular ring, kind of like the polar lights there, maybe, of activity.
yeah, maybe. Well, that depends a lot on how the magnetic field of Earth would react to that. Because
Right.
one of the ideas that they propose, it's what Johnson calls the multiple scenario, would be that these currents would be so strong that they would basically depolarize the magnetic field of Earth, and
Right.
would create this multipolar, really screwed configuration of the fields, which would obviously kind of bring a lot of chaos to it, so to speak. So those discharges might occur anywhere. Uh, okay, so that
Fascinating.
was,
Please continue.
yeah, that was this idea that I really liked, and I thought that, like, wait a minute, but what if the same thing can occur even in like calm space weather conditions, like without any extreme CMEs? So I thought that since Van Allen belts kind of shield our planet roughly in this latitude range, let's say like 63 to 63 or something like that, but at the same time, higher than that, we actually connect with magnetic field lines to the solar plasma. So I thought, well, what if there's something like that going on? Like there is this field-aligned current going in on one side and going out from the other side, maybe, but it's kind of locked. I mean, maybe these currents might go through the crust, and that's why we have these latitudinal dependence, because at 63 they connect to the sun, but in between they might go through the crust. So that was my idea. And maybe, and again, it's just a geometrical intuition, let's call it that way. I
This
don't have a mechanism of how that might work in real life.
I do apologize for the interruption again up front, but this ties in very neatly with Bruce Laybourne, who talks about these telluric currents going up through the mid-oceanic ridges, making a circuitry there, basically. So I'll point that work out to you later on.
Yeah, yeah. And by the way, in this type of approach, we might say that what we call the plate boundaries, they might be actually the paths of previous discharge that have not yet cooled enough.
Actually, and this is maybe too much for now, but Bruce Laybourne points out that it seems that those mid-oceanic ridges, the plate boundaries, if you will, are the pathways, kind of like an electric circuitry, like a wire, if you will, the conductive zone. And they seem to flare up and fire up, connected to space weather, etc. And that, again, is connected to, you can detect those deeper telluric currents, I call them for now. I'm not even sure about that, but those deeper currents, you can detect them through the radio spectrum, so radio waves, and they occur about a day before earthquakes actually happen, for example.
Well, so, that's pretty cool.
Yes, and there's a whole bunch of work there. That's why I made the connection to Bruce there.
Well, thank you.
Ties in really neatly with this picture. Sorry for the interruption. Please continue.
No problem. Well, I've been searching in the recent couple of weeks for what kind of observational data we might have in order to, confirm or falsify this kind of model. But so far, I haven't really digged into that a lot. But I wasn't aware that we can actually measure the telluric currents. I'd have to look into that more. Yeah, that would be, that would be just perfect if we could see the current itself right away. Yeah.
Right. We'll go into that later on. Sure.
Okay. Well, that's just another illustration of the same thing, basically. So again, we connect to the interplanetary plasma higher than 65 or 63 latitude, roughly speaking. But these strong earthquakes only occur in between that. So maybe there is some connection. Okay, so it was the strongest earthquake of recent couple of years. The quake in Mexico in 2017. It's just maybe it's another possible indication that some sort of additional current was observed back then, because what I've noticed, and I just noticed that just completely by chance, let's say, that roughly like 20 minutes before the earthquake, the Discover satellite detected this spike in proton speed, solar wind speed. And it's keep in mind that it's Lagrange L1 point, which is more than 1 million kilometers away from Earth. But it just turns out that 20 minutes is roughly the time that would be needed for these roughly 1,000 kilometers per second protons to reach Earth from that point. And even more so, it would seem that it's the data from GOES satellite. I found that there is a definite spike here. Of course, it's not as pronounced as these ones, but it's there right during the earthquake. So it might indicate that actually these protons arrived right here, and it coincided with the moment of earthquake. And I should note that, of course, you might consider this just being an artifact because it really kind of stands out. But what if it's not? I mean, you don't see solar wind speed 1,000 kilometers per second. It's just insane. I don't think I've ever seen something like that. And it was very high even before that. Look, you see 700, 800. It's basically unheard of, at least for that stage of the solar cycle. So maybe it's related to that earthquake. But what is also might be related to that time, September of 2017, is this Oumuamua, this interstellar asteroid, or at least supposedly interstellar asteroid. So a lot of people have asked me, like, if that's a real picture of the object. Well, I think it should be obvious from that picture that it's not. That's what we saw. That was a Hubble Space Telescope. It's basically the best picture that we have of this object. So in case, okay, so I did several videos on YouTube for Thunderbolts project. So I think that most of you are at least aware of that. But anyway, I was just for this talk, for this presentation, I wasn't going to focus on that. So I just gave these links. So yeah, so what is interesting about all this story is that, and again, it's 2017, okay? So on September 6th, we've had the strongest solar flare in 12 years, basically in the whole cycle, if you like. And we've had a really high sunspot area. It's usually measured in millions of the area of the hemisphere. So it was like that. And it supposedly, I mean, okay, so a couple of days later, we've had this Mexico quake, again, which might have been related, to this whole space weather that we've had at the moment. But at the next day, on September 9th, according to our retro calculations of its orbit, there was a perihelion of this Oumuamua thing. You see, we've only spotted it in late October, so we don't really know what it was doing before that. But if it was, more or less moving according to Kepler's laws, I mean, it had some peculiar acceleration, but it wasn't that big. So maybe it was, really closest to the sun on September 9th or something like that. So, of course, kind of, the usual idea in EU community is that maybe it's the close approach of this object to the sun is what caused this whole spike in activity. And that was my idea initially too. But then I thought about it a little bit and I thought, well, wait a minute, but what if actually the object itself was ejected by the sun during this spike of activity. And I don't think anyone has proposed such an outrageous idea before me. So it's a thing would be a really interesting thing, because I mean the properties of this object are really strange. Like it seems to be really light because it can accelerate outwards from the sun, and so on and so forth. And so there's a lot of peculiarities about it. So maybe it's some sort of, you know, weird piece of matter that we're not used to be dealing with, that could have been produced through some unknown process on the sun itself. So it's an interesting thing to look into. And you all probably already tired by me telling you this. I mean, this thing that I found, that the orbit of Oumuamua is aligned to the interstellar magnetic field vector, and in particular, the interstellar magnetic field vector lies in the plane of orbit of Oumuamua. So, and again, I've discussed this in much more detail in these videos for Thunderbolts. I wouldn't say much here, but I would just make a couple of comments. Like, okay, if we think that it is an interstellar object, really, so it really was following this hyperbolic trajectory. So it entered the solar system roughly here, almost at, you know, from the solar apex direction, and then it swung by the sun and went somewhere there. Then it might mean that interstellar magnetic field plays a huge role in the way that these objects move. Well, because obviously, if it's an interstellar object, it spent a lot of time in this, you know, interstellar magnetic field. So maybe it impacted its trajectory in a large way. And obviously, that would contradict, you know, the regular Keplerian gravitational-centered approach to these things. But at the same time, what if it was actually ejected by the sun? So there was no this first part of its trajectory was not present, but it was just ejected and went somewhere there. Then maybe the alignment of the plane of this orbit with the interstellar magnetic field would mean that it's actually the interstellar processes, some sort of processes. I'm not saying I know the answer to how exactly it might work, but some sort of interstellar processes has led to this spike of solar activity. And that's why the thing that was ejected during that activity, its trajectory was also aligned with the interstellar magnetic field direction. That's kind of the idea. All right, so this is the part about the interstellar filaments, but I'm not sure if it's reasonable to talk about it in detail, because, I mean, we've had this 3-hour talk with Jim. So I'll probably just skip that, if you don't mind, or I don't know. Well, I don't really know. I mean, we haven't yet even posted that, you know. So.
Right.
No, but if there's a 3-hour session on it, you could skip it, right?
Yeah, and we're already like an hour and a half into this, so yeah, maybe it would be reasonable.
It's up to you.
I just don't. Okay, so I'll just say a couple of words, you know, like literally what I was talking about there. Okay, so I gave these citations for, you know, Don Scott's papers, where he derives this model of how, you know, force-free field-aligned current should behave. Okay, and I'm saying that most of what I'm going to be talking about is about Jim's ideas. So these are just, you know, a few snapshots from Don Scott's papers. So this is the cross section of the current. It's again also the cross section, but it's kind of in 3D for the magnetic field strength and the current density. And these are some other graphs, like how magnetic field depends on the distance from the axis, how the current density depends on distance from the axis. And here I want to note how similar it looks to this other paper, Remember that paper about the potential of interaction of alpha particles and nuclei? Like just it almost looks like the same type of, kind of sort of Bessel-like function is there. So maybe it's somehow related, even though there's a huge gap in between them, like 10 to the power of 30 or 40 in terms of spatial scale. But I mean, who knows? And it kind of, again, relates to this whole issue of scalability. So we've talked about this local chimney a lot, which again, Jim considers to be an example of such current that we're in. And then I give just a few pieces of evidence for that might be the case. Remember that we've discussed this temperature of Arcturus that mysteriously rises in quite a significant degree, which might be related to its motion with respect to this current. I mean, it's just not normal for stars to change in such a time frame. Like, it's less than 100 years, and you have almost like 30% increase in its brightness, in its temperature. And there's also reports of ancients of Sirius being a red star, which also might be related to something like that. And there are, these points that we've discussed in much more detail during our 3-hour session, the problem of precession, the parallax, chemistry, like, the separation of elements in the current might be the reason for that. The red shifts and blue shifts that might be caused by some sort of interaction of light with plasma. This Gould belt, this is the toroidal belt of stars that basically rotate around the axis of, or roughly around the axis of this current, and various other pieces of evidence. I really don't feel like diving into this in more detail. Okay, so here I've had a kind of a philosophical comment again that, well, we've discussed that also during our podcast, that, one could think that cyclicity kind of contradicts catastrophism, because kind of almost by definition, a catastrophe is the breakup of over regularity, essentially. But at the same time, we can see a lot of examples of systems where it's not the case, where, kind of local catastrophes might be part of a larger cycle. That's the basic idea. So an example, again, would be, at least one of the possible examples would be the solar flares and sunspot cycle, where the solar flare is like a sudden burst of energy, a catastrophe of its own, so to speak. But at the same time, it's just a part of a sunspot cycle, and it doesn't really break it. It doesn't really do anything to it. Okay, so I've had this idea, like, Velikovsky squared, that, Velikovsky talked about celestial catastrophes, but maybe there are cycles of those which should be related to larger scale processes, again, these interstellar filaments and so on. So here I've discussed briefly the possibility of detection of these currents. And again, we've talked about that a lot, about synchrotron radiation, about Faraday rotation, and so on and so forth. And we've talked about even the question of how can we measure anything at all with our, little space probes? We can't really, measure potential difference even in the solar system between, let's say, the orbits of two planets or something. So, but this is kind of the important part, and I think I should make a comment here. So I believe that it might be productive to go that way. So there is definitely a lack of how would we say, a lack of a good informational product in the observational part, which means that we need to map, all these structures that, like this interstellar, local chimney, the nearby stars, where they are going, and how it all is oriented with respect to each other, with respect to planets, and so on and so forth, with respect to the galactic plane. So this is an important piece of work that should be done. And I hope that in the coming months we'll do something in that respect with David and Jim. But there's also a theoretical part that should also be developed. Like, okay, Don Scott has a model for one filament. That's really cool. But what if we have, you know, two filaments like spiraling around each other? That's basically not described in, at least analytically. I mean, Peratt did some, you know, numerical simulations and so on, but we don't really have a working model of how this should look like, what kind of consequences it should lead to, and so on and so forth. And that's kind of the second part of the puzzle. So if we'd be able to also develop this kind of model and also really map everything around us really well, we can then compare that and maybe infer, you know, maybe we'll basically see what's going on around us. So maybe it would give us some hints for, you know, whether we are correct, what kind of improvements we should make to the model. Maybe we are wrong in the first place, you know. So those are really kind of hard questions. Okay, so this is another thing that I did in my modeling thing. So I just mapped the direction of this chimney axis to see if there's something would surface. And I've noticed a really interesting thing, like here again, this interstellar magnetic field direction. It's the local chimney axis. Orange is the plane of the solar equator, and blue is the plane of galaxy, right? So you might notice that the solar equator and galactic plane, and by the way, this arrow is the spin axis of the sun. So you might notice that the direction towards the galactic center kind of lies not very far from where these two planes cross, the solar equator and galactic plane, okay? Well, that's one observation. But what if we add another plane that goes through these two directions, the local chimney axis and interstellar magnetic field? Now, of course, this plane doesn't really correspond to anything physical, like it's just an abstract mathematical construct, if you like. But I've noticed this amazing thing that all these three planes, like the galactic plane, solar equator, and the plane with magnetic field and chimney axis, they all cross almost on the same line that's really close to the galactic center direction. And it's quite amazing. I mean, if you take three random planes, they shouldn't cross at one line. That's just ridiculous. I mean, you would have like three lines of their intersection, essentially. Like if you take a coordinate planes, the plane with x, y, x, z, and y, z, they cross at right angles, actually, right? Mm-hmm. So it's not one line, but here it's one line, and it's quite amazing.
Trifecta.
So, yeah. So in my opinion, this indicates that their alignment is not random. That's what I'm saying. So solar equator is not randomly oriented, but somehow, and again, I'm not saying I know how it works. I'm just noting something strange is here, that somehow the solar equator is aligned in such a way that it crosses these two other planes, the galactic plane and kind of, you know, local interstellar plane, let's call it that way, so that all three cross in the same direction, which is also peculiarly enough pretty close to the galactic center direction. So in my opinion, this is kind of although, I mean, it's not a point in itself because it doesn't really tell you anything, but in my opinion, it's an indication that something strange is going on, basically. That's what I'm saying. So our local chimney is not unique. Like, for example, this paper describes more chimneys in about 10,000 light years away. Then we have this double helix nebula, where it's basically two filamentary currents dancing around each other. And what's interesting also is that it's also kind of perpendicular to the galactic plane. And even the paper itself says that it might be a part of a larger structure. It's also kind of neat. Yeah, it's just a joke that I saw Robert posted. It's from this channel on YouTube. And here I've advertised our channel, and I've just, to be safe, I know that it might be renamed, so that if people would search for it later. Oh yeah, and here I've also said that, I've mentioned these skeletons that we have here, because there was another comment at the Thunderbolts Project YouTube channel, which I really liked, so I took a screenshot from it. It's under one of those videos about Oumuamua, so you can read that if you like.
I don't think it looks like a zombie. Gene,
huh?
They did Gene Wenninger, but
yeah, well.
But the skeletons were somehow they popped out of nowhere, but and then the view thing, so, and then the view happened. So there's a lot of crazy synchronicity. The view actually happening is bizarre. So.
I just found it hilarious, and so sorry, Jim, for screwing of your name by this guy, but. I just think it's really interesting. Okay, so this is the last section of my talk, basically, and here I talk about cycles. Okay, so why do I talk about cycles? It's because, well, basically my argumentation for it is that you can consider a cycle being a structure too, but it's a structure in time rather than in space. If you have a periodic repetition of something, it's almost like, a one-dimensional crystal lattice on the axis of time, if you like, so that like something repeats itself with regularity. Temporally speaking, so that's my justification for that. And we've discussed this a little bit on one of the podcasts, that there is this book by Schnoll, Cosmophysical Factors in Stochastic Processes, and it's actually available online for free, so it's pretty cool. So I find it maybe one of the most important works that has been done in terms of this cyclicity stuff. So what he deals with there is basically the measurement, the theory of measurement, and even more so the practice of measurement, so to speak. So according to the theory, again, supposedly, if you make an infinite number of measurements of something, like literally anything, like the length of your table, let's say, so you make an infinite number of measurements of that. Of course, you cannot do the infinite, but a very large number of measurements. You should get this sort of a bell curve where the x-axis is the result that you get, say the length of your table, say the mean value is, I don't know, 2 meters. So you get and y-axis is the frequency of how frequently you get this result. So let's say the mean is 2 meters, and the farther you go up or down from 2 meters, like let's say there's 2.05 meters here, and here you have 1.95 meters, and so on. So it falls off like that. So there should be some mean value with maximum probability, and so on. So this Gaussian curve should appear, again, according to the theory. But the problem is that if you do that in real life, most of the time, you get something like that, or you might get something like that, which doesn't exactly look like what you should get, according to the theory of measurements. And believe it or not, I actually encountered insane results, where the mean value was actually 0. There was no single, measurements corresponding to mean value, but there were, some weird peaks and troughs here and some weird peaks and troughs here, but they still painted this bell curve around it, like there was some mean value, even though it wasn't detected a single time. So it sometimes gets really awkward and really stupid. Right. But what people do is they average this thing out, they smooth everything out and so on, and still infer this curve, this bell curve.
Right. It's most famous for blurring, in images. So just interesting metaphor.
Yeah. So what Schnall said is that, wait a minute, but maybe this is important. Maybe we shouldn't discard it at all. And even more importantly, he found that this fine structure of the statistics of measurements, it depends on the time when you're making this measurement. Now, obviously, you should be really precise. Like sometimes, like you really should have a good precision to measure that, because the very width of that whole thing might be pretty small. But anyway, this is what was later called Schnoll effect, but by other people that worked on this problem. That again, it's the fact that this fine structure of measurement depends on the time of day, of year, and so on. And so what's even more interesting is that it seems like that all kinds of random processes, let's say, of all kinds of measurements depend, have kind of the same statistic, the same structure of statistics if you make them at the same time. So here are a few examples, like, and again, that's all from his book. Like, for example, discharge latency in a neon lamp and electrophoretic mobility of lattice particles. You can see that, well, they're not exactly the same, but they're very similar, the statistics of these measurements, right? And some other examples, like, beta decay of C14 and some other parameter measured here, and some other things are measured here, so on and so forth. So it's a really peculiar find, and I find it really, it's really important to acknowledge that, and to keep that in mind. So here are some of the periods that he identified, like, the periods of repetition of these patterns, right? So, and they all correspond to some sort of motions of stellar bodies. Like, we have days, months, years. And what's interesting is that even half of the day and half of the year is also kind of a period of its own. And we'll see that a little bit later. It's kind of a spoiler alert here. So I believe that if this is actually the case, and I have no reason to not to believe him. I mean, he's like not some crook. He's actually a really recognized scientist, and he worked in biochemistry initially, I think. So he studied, the folding of proteins and things like that. That's where he discovered that initially. But later he has done some tremendous amount of work. Like, he's been working on this for half a century, basically. But he's also quite an accomplished scientist outside of that. So I don't think there is any reason to doubt his work. But of course it might be wrong. I'm just saying that I believe. That's my point. So I think that this might be a genuine foundation for some sort of new astrology. I mean, if really physically something happens and we might measure it and it depends on the time, well, that's exactly what astrology says, right? Like, one moment in time is different from the other because there is a different configuration of celestial bodies. And there are also cycles on top of that correspond to the motions of celestial bodies and so on. So why not? I think it's a very reasonable, conclusion that might be done here. Okay, so a couple of other interesting cyclical things. Like, for example, this paper describes the detection of an interesting oscillation, 5.9 year period of the length of day variation. So the length of day actually slowly increases, but not only kind of more or less linearly increases, but there is also an oscillation on top of that linear increase. So you might subtract this linear trend and get just purely this oscillation. That's what they did here, all right? So they found that it's not a very big change. You can see 0.1 millisecond roughly, plus or minus, but it's detectable. I mean, we can see that clearly. So again, 5.9 year period, some strange oscillation, okay? And kind of related to that is this other paper where they, well, you've probably heard of the problem of measurements of gravitational constant in the lab, which you can see here that our precision is really poor in terms of determining the gravitational constant, like 0.1% accuracy or something is what we have for gravitational constant. And that's really bad. I mean, it's one of the fundamental constants. So now, in case you're wondering how are we able to launch space probes with that poor precision? Well, it's because people don't use gravitational constant per se in astrodynamical calculations, I guess, astronautical basically. People use what is called the gravitational parameter, which is this g times mass of the planet or the sun or whatever else. So they don't need the constant itself to make these calculations. But we know, again, there is a big problem with constant itself. You can see that these measurements really cannot be, some of them are almost like mutually exclusive, But what these guys did is they said, well, what if we try to approximate this with sine curve? Because why not, right? And so what they got looks not very good. I mean, there are some things that are not in this how would we call it,
mapping
corridor, yeah, but still it looks pretty decent. But the most interesting thing was that it is exactly the same curve as this one. It's exactly the same period, 5.9 years, and it has exactly the same phase. So it's like you just take this curve and just transplant it here, and it was their best fit, the best fit that they found for these measurements.
What are
now,
the
of course, huh?
What were the measurements? The red dots.
What do you mean? What?
What I mean, what are they? What are they measuring? Just
the gravitational constant. I believe it's something like maybe what Cavendish did. Maybe some sort of well, how do you call it? That like the rotational balances with masses or something like that.
Okay, so like each of the names are like different places where they were.
It's a different measurements of the G constant that have been done in the last 30 years or so. Got it. So, and they found the same curve here. Now, of course, you can say, well, okay, maybe it's somehow related to, if the length of day changes, that means that the centrifugal force changes, and that might impact all these experiments in some way. Well, that sounds reasonable, but it doesn't exactly gets rid of the question, well, what causes this 5.9-year oscillation in the length of day in the first place, So, and there's no answer to that at the moment. And it's really interesting. It's a really interesting thing to look into. But even more so, remember we've discussed the neutron lifetime measurements. So there's this so-called bottle method where you pour neutrons. And again, this is what is called the free neutrons, right? I've mentioned that maybe neutrons don't exist inside of the nucleus, but the free neutron is kind of a totally different beast. And it's still a subject of discussion, what the hell that is in the first place. But okay, well, according to standard particle theory, neutrons exist. So they pour it into a bottle, essentially. Well, it's not exactly a bottle. There's a very complicated system with huge magnets and stuff. It's just a very simplified depiction of it. Or you can just shoot them through, again, magnetic coils and things like that, and just look at how many of them decay. So here you look at how many remain after a certain time, and from that you infer the lifetime of individual neutron. But here you're shooting them through this tube, I guess, and you just look at how many of them decayed while they were traveling there. So you're basically comparing the number of input versus the number of output of neutrons. All right, and the problem is that these measurements give quite a different results. Here it's not even 0.1% error, it's 1% error, essentially, like roughly 8 seconds. or difference between these two methods, and that's quite a serious problem, and people don't know what to do with it at the moment. All right, but so and I was just out of curiosity. I mean, why not? I just took these papers with the more recent, measurements of this neutron lifetime thing, and I just took everything here with anything with decent precision, which is, it's not exactly decent, but so I took these results of these measurements, and I just said, well, what the hell? Let's just plot the same, curve here. And I've tried to be modest in terms of, the amplitude of it. But I would say that it looks not that worse than what these guys have got there. And again, the beauty of it is that it's the very same curve with the same phase and the same period. So it's just like I just took this thing and just plotted it onto this graph with neutron lifetime. So maybe it is related to that also. Now, of course, yeah, I understand. Might look not exactly cool, but there are also issues, with the publication date, because I only took, when the paper was published, but obviously the experiments were done a bit before that. So I wasn't very precise with all of that. Let's put it that way. But who knows? Maybe it's actually something that's going on. Well, now the question might arise. Well, what the hell is 5.9 years? Why do these values seem to oscillate with that period? Well, obviously, this is half of the orbital period of Jupiter. So I thought, well, maybe Jupiter is somehow involved. Like, there's this paper that describes how when we are connected to Jupiter with the magnetic field lines of the solar wind, we can actually detect the cosmic rays from Jupiter. Like they just travel all the way from there, using these, magnetic field lines of the solar wind as a highway, so to speak, and jump onto our planet. But the problem is that it happens roughly every year, like 1.1 year or something like that, because we're moving pretty fast and Jupiter is pretty slow. It's not 5.9 years. So what then causes this 5.9 years oscillation? So I've plotted where Jupiter was. Like I just took all these, this curve basically. I looked where its maxima and minima were, and I just plotted where Jupiter was during these maxima and minima. And what I got, and again, maybe it was a mistake, but I kept all these planes here. So what I got was that Jupiter was somewhere here at maxima, and again, half a period later, again here at maxima, and at minima, it was somewhere here, and again, half a period later, somewhere here. So you get this sort of a cross here, right? And the most interesting thing was that at maxima, it's really well aligned with the galaxy and the sun. So at maxima of these curves, Jupiter is sitting at the line that connects the sun and the center of the galaxy. And at minima, it's exactly perpendicular to that line. So my idea about, you can see it's really amazing. I mean, it just cannot go any closer than that to the galactic center. Just because of the tilt of its orbit and so on. So my idea about what causes this, and again, it's a hypothesis at the moment, is that maybe when Jupiter is on this line, it causes, again, displacement of the sun. Because Jupiter is the biggest perturber of the sun, just in gravitational sense. So maybe it causes some sort of motion of the sun along that line. Well, it's not even maybe, it does cause such motion, but maybe it causes some sort of external influence on the sun that later, manifests across the whole solar system as, the difference in these neutron lifetimes, some sort of effect on Earth, length of day, and so on and so forth. But when it's perpendicular to that line, it's some sort of other influence. But we have a mean value when it's not really aligned and not really perpendicular, in this kind of X shape in this case. So that's kind of the best bet, my best version of what's going on. So I think it's the cause of all this is the displacement of the sun with respect to larger scale structures because of the influence of Jupiter. That's what I'm saying, basically. Right, and some other interesting things that I've found recently, like it has been known for some time that the flux of solar neutrinos has this peculiar 26 months period. And what's interesting is that this paper that I was citing, this one, they actually clearly say that we have no theoretical reasoning to resolve this periodicity. And well, I just wanted to note here that 26 months is actually the synodic period of Mars, which is, you know, the period in between of the same configurations of Earth, Mars, and the Sun. So maybe, I mean, Earth is like the most massive planet in the inner system, and Mars has a pretty eccentric orbit, so it moves back and forth to and from the Sun quite a lot. So maybe their combined influence on the Sun causes this, or something like that. But
Eugene?
yeah.
What is the official standpoint on this effect? Because this effect would imply that nuclear decay, in this case neutron decay, for example, would be a result or at least influenced by external factors. But to my knowledge, that is not acknowledged right now.
Yeah, well...
Can you speak to that?
Well, what these guys saying is that basically we don't know what's going on, and that's their answer.
Right.
I mean, well, basically they're saying that something inside the Sun has this cyclicity. So, you know, but what exactly is going? I'll show you another paper a bit later that tries to go farther and actually give you a possible explanation. But this one doesn't do that. They just say we don't know what's going on. And that's
okay,
it.
So it's, that question is not addressed, if you will.
Yes,
Okay.
I would say so.
I have a question. These are solar months, right? Not lunar months.
What do you mean here?
Yeah, like these calendar months, 26 calendar months.
Oh yeah, exactly.
Okay.
Yeah.
Okay.
Mm-hmm. So all right, so this is this other paper that I mentioned. So this guy, he actually goes farther than that, and he tries to, you know, just take a basically Fourier decomposition of the flux of neutrinos in order to, you know, find other periods. And so by far the strongest signal he gets is with the frequency of 11.85 times a year, which roughly corresponds to 31 days. I mean, the period is roughly 31 days or something like that. So, yeah, so, and this is a really strong signal, like there's a strong periodicity with that time. And the other period is kind of close, you know, the second strongest. So it's really a strong signal right here. The neutrino flux from the Sun seems to kind of almost like switch back to the beginning, so to speak, every 31 days or so. And what this guy is saying is that, well, he obviously, I mean, what the only instrument they have is, you know, some sort of internal processes in the Sun. So that's what he tries to use. He says that there may be a second inner tachocline separating the core from the radiative zone. There may be an inner dynamo that could produce blah, 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 and a second solar cycle. So he basically tries to introduce this ad hoc second solar cycle inside the Sun. It's the second tachocline, you know, this layer that separates basically the outer layers that have differential rotation and the inner layers that are rotate like a solid body. So because they don't have any other instruments other than that, you know, it shouldn't be an externally driven process, because that would ruin the whole nuclear physics and so on. So, but that seems kind of far-fetched to me. It seems really like an ad hoc thing, because we don't see any other manifestations of this second solar cycle, and so on and so forth. So it looks really suspicious, but well, it's something to look into, I would say, yeah, to sum it all up. But what I've also mentioned during my talk, and I want to repeat that here, is that, again, kind of returning to this issue of astrology, like if you look at this number, like 31 days, it's basically a 30 degrees of motion of the sun in the sky, or the Earth in its orbit. And that basically corresponds to one sign of a tropical zodiac, if you think about it. Not exactly, of course, but really close. I mean, if it was exactly, it would be 12 times a year, not 11.85. But it's really close. So it's almost like and we can actually measure that. It's not something that I've invented, you know. It's something really changes on the sun, and we can detect that. So it's not some fantasy. The problem is how it works. Well, that's a good question, and I don't know. I have no answer to that.
What I'm no astrologer at all, but what you're describing, as far as I know, astrology points out that the sun is always the source of and all the attributes that we assign to the certain houses or the celestial sciences and stuff. But it's like a colorization of that source, right? It's an influence on the source that is always there. And then you become the lion or the bull or the twins or whatever. But what you're pointing out here, Eugene, in my mind, again, this is fascinating. What you're pointing out is that we can actually overlay these trends and these day and periods of astrology and actual influences in astronomy, if you will.
Yeah, I mean,
that's what I hear you saying. It's utterly fascinating.
Yeah, well, the most fascinating thing to me is that it's, you know, it's serious dudes with serious detectors that are telling us that there are periods like that. And they are also telling us that it's really hard to explain.
Right.
Maybe even impossible to explain at the current moment. So that's definitely something to look into. We should keep that in mind. That's what I'm saying.
Astrology
and again,
almost seems to be a quite delicate system, if you will. It's nuance, it's finesse, it's the little jittering of the bigger system, as you pointed out with the Coulomb force, right? On average, it's a nice going down curvature, but if you look more closely, you see that wiggling there that you pointed out.
Yeah,
right?
exactly.
It is as if the astrology is that little wiggle, the nuance.
Oh, maybe, yeah. Okay, so, all right, so it's just a sort of an aggregate of what I found on this topic in recent years. Like, okay, so there have been a bunch of works that describe the possible variability of alpha decay, beta decay, and so on and so forth. But I should note here that they are talking only about these mean values, you know. They so they wouldn't be able to see these Schnall type effects, you know, the finer structure of statistics. They're kind of ignoring that altogether. So, but still, even given that, there are some papers that say that there is variability of decay rates. And actually, like one of these papers, it actually says that it seems that neutrino flux from the sun determines the decay rates, like beta decay rates. And it's really an interesting thing, and I think that Eido, you might be interested in that. But at the same time, there's a whole bunch of other papers that says, well, you know what, there's no variability whatsoever. So, like, again, kind of long story short, like if you want to prove somebody that there is variability, you take these papers. If you want to prove to somebody that there is no variability, you take these papers.
Well, that is the statistics comes in there, right?
Yeah.
Statistics can be put towards your liking a little bit. Yeah.
Statistics might be nasty. Yeah. That depends a lot on how you process your data and so on and so forth.
Exactly.
Well, I guess the point I'm trying to make here is that it's not a settled issue at the moment. Like there is indeed some indications that there might be variability of decay rates, even the mean values of those. Not even talking about, you know, this finer statistics that Schnoll is talking about. Okay, so this is pretty much the conclusion to the whole presentation. So in the first part, I was talking about this Alphane's triple jump, and I proposed kind of this fancy pants quintuple jump, like to consider electromagnetism being the key force all the way through from cosmology to, you know, quarks and electrons. And again, it's not really a new idea, but my purpose was to kind of give some new evidence to that, let's put it that way. And it seems that many phenomena in nuclear physics and particle physics might be explained through the emergence of some sort of structures due to the, well, let's say, self-action of some sort of electromagnetic field or something like that. Then we talked a little bit about this extended gold scenario of earthquakes, where these, you know, kind of magnetic structures, let's call it that, might cause some currents that might lead to earthquakes and so on. But again, the details are unclear. It's more of a geometric intuition at the moment rather than a physical theory. Then I've mentioned my research into Oumuamua, this interstellar asteroid. I've noted that its trajectory is aligned with the interstellar magnetic field direction, and that its very appearance might have been caused by the solar activity in the first place. So it might not actually come from other stars, but it might have been ejected from the sun. And again, I'm not like 100% committed to this hypothesis. It's just a thing that I haven't found anyone else to be talking about, so that's why I'm kind of peddling it a little bit here. But I would be perfectly happy if it would be just an interstellar asteroid. It's not a problem with me. So yeah, then we talked about Jim's research, about the evidence for a solar system to be traveling along this local chimney, which seems to be kind of like Don Scott's Birkeland current. And then we talked about cycles and, you know, possible implications of larger scale spatial ordering in terms of temporal ordering. Like, you know, again, the perturbations from Jupiter to the sun might cause it to wobble back and forth with respect to this larger current, and maybe that's what causes the solar cycles. Maybe that's what causes all these really mysterious changes in Earth rotation rate, in neutron lifetimes, and so on. But of course, I'm not even nearly saying that I understand how it works. It's just an intuitive, you know, kind of trying to put things together at the moment. And this is my belief that research, kind of like what Schnoll did and so on, it might actually lead to some sort of renaissance of astrology. And I'm not saying that because necessarily I have, you know, some stakes in it, so to speak. I'm just saying that it's the most logical conclusion that might follow from that, in my opinion. And I have nothing against it in principle. Okay, so and this is kind of the final comment that I want to make here, is that it seems from what I've shown you, one might conclude that, okay, you know, there's this regular reductionist approach that, you know, you just add parts and you get a whole, so that, you know, the properties of atoms would follow from the sum of properties of quarks, electrons, and whatever, and their interactions. So you kind of climb this ladder upwards, so that, you know, the cosmological processes are determined by the sum of lower level processes. But at the same time, I would say that what I've shown you today might indicate that there is also a backwards motion here too, that the displacement of the sun, for example, with respect to the galactic plane and so on, seems to cause some perturbations on like super microscopic level. So in general, it almost looks like there's some sort of feedback loop, you know, where like microscopic processes add up to form macroscopic processes, but at the same time, the very behavior of microscopic particles is predetermined by larger scale processes. So it's almost like there's this feedback loop where, you know, micro determines the macro, while macro determines the micro. And obviously, kind of the problem that is with all of that is that we're not really ready to deal with something like that. You know, there's this reductionist approach where you go from bottom up. There is holistic approach where you go down. You know, but to integrate it all together, I don't think we're ready to do that. But at least, you know, to acknowledge the possibility of that is a very solid step forwards. Well, okay, I think that's all. So thank you guys for attention.
Yay. Excellent.
Thank you for talking.
Beautiful presentation, Eugene.
Okay.
It's nice to see it in more detail.
Excellent work, Eugene. Absolutely fascinating. And that last remark, I'm on board. I see that happening, that interaction between micro and macro, up and down. Totally.
Mm-hmm.
Awesome presentation. Very nice.
So do you have any like feedback for some more particular points? Or well, it was very long, so I'm sorry for that, but I wanted to expand a bit more.
Let others speak first. I made a few notes. Maybe we can later on during the week, somewhere down the week, Eugene, if you see a moment there. I would love to go into this, but I feel I would need at least an hour there with you, probably too.
Yeah, well, that's no problem. I mean, I would be happy to hear your insight. Yeah.
I would like to go into the nuance there for a moment, which you started out. Let me say this. I mean it. You did an awesome job by how you build it up. Lots of fundamentals. Coming back to the fundamentals later on. Pointing out. You pointed out the controversial things very nicely, I should say, right? And you made a very strong case in my book for there must be much more structural things going on than we right now recognize, right? That's why they heard loud and clear. I would love to go into the number of quarks, the number of free in connection types, right? I would like to go into that much more. The Rutherford experiment with free neutrons, maybe something like that has been done before. I would like to go into that, and there's a lot more.
Yeah, you know that there's an interesting branch of neutron physics that is called neutron optics, essentially. And what people do there, you see, if you have it cold neutrons with like very low energy, like, you know, room temperature energy, so to speak, like 0.0 something electron volts, you might actually see through, you know, this de Broglie relation with wavelength, I mean energy, momentum with wavelength, that these cold neutrons would have a wavelength roughly the same as the visible light. So there's a whole branch of neutron physics called, again, neutron optics that kind of almost uses the same devices that you use in optics, but for these cold neutrons, you know, like diffractional, how do you call it, grids or
so
well,
that,
you know,
so
lenses and so on.
If a neutron, a very slow neutron, would fall in the spectrum, in the spectrum as in blue light, right? That would be equivalent to that amount of energy, if you will, right? As in kinetic energy. So that would be very gentle interaction, if you will, still leading to a neutron being absorbed by a nucleus, for example, right?
Yeah, it doesn't mean you can see them, because obviously, I mean, your retina doesn't work that way. But yeah, they behave pretty much like waves of visible light, and that's pretty peculiar.
Interesting.
So I'll tell you what. It's yeah. Anyone else want to put a question on the table, or that the silence seems to indicate.
I wanted to say I really like the and showing the I don't know how you would talk about it, but it was in the video you were talking about the Schnall effect. I just wanted to say though that it looked to me, and it just could be my eye, like there might have been a more high frequency and higher uniting those events that you had plotted yourself, and maybe it's possible that there's more than one of these greater periodic waves, and it may be that we just don't have enough of these. They're too many years apart, and we don't have enough data to find that wave. But I really like that you saw that wave in there. And I personally believe in the variation of the so-called constants, and that the change in measurement is a real and an important issue that is, I guess, swept under the rug. So I like that you've put a lot of time into actually getting these measurements and showing, or at least following an intuition that there might be some very regular pattern to that, and that it is related to the magnetospheres of maybe the sun, maybe Jupiter. I guess you mentioned even Mars. That makes sense to me. As for like a new astrology, I think that falls right in line with a lot of the thoughts I've been having about new medicine and new religion, that there will come a time when the effects of this greater system upon our existence will be self-explained, that we will gather enough data to show those effects, and it will create some kind of new understanding, right? I have a book on lunar astrological observations of the Chinese, and the measurements that they were doing were extremely complex because they couldn't find a perfect regularity. There were always little wobbles and little changes to the behavior in the moon. And yet it was incredibly important. So they spent a lot of resources of the imperial governments of those times trying to keep track of how the moon would behave, because they were, of course, they had a bad hypothesis with the eclipses being related to the emergence of comets and such. But the effect of that might be incredibly important for our health and for things like the economy. I mean, just think of the effect of when people, I don't know if people have had this experience, but everybody wanting to go out and shop the same day, and then the traffic is just terrible, but it's just so beautiful out that everybody wants to go out at the same time. So then the effect that would have from year to year on economies, whether they spend money or they feel basically bullish or bearish, and finding ways of making predictions for that. I think that there could even be big money eventually spent in that. I don't know if it'd be this decade or this century, but it seems to me that is the likely outcome of gathering enough of this data, and you're right at the bleeding edge of the front of that.
You actually reminded me of one thing that I haven't included where I probably should have, and that is maybe, you probably weren't on those podcasts, but I've mentioned another paper that discussed a influence of, or at least, correlation between the solar activity and like human mood. Like what they did in that paper, they've analyzed the so-called Twitter happiness index or something like that, where just and it's, by the way, it's available online. You can look it up. Like people are doing constantly content analysis of Twitter posts, like of, tens or hundreds of thousands of them per day, probably. And they just rate the kind of the total mood of the day, so to speak. How much like negative words were there, how much positive words, and so on. And so the guys in this paper have found a negative correlation between the solar activity and this Twitter happiness index. So at solar minima, it seems like people are in general more happy than at solar maxima. And it's a really interesting correlation, which again might in some way be related to whatever, I don't know. I have no idea how it might work. I mean, maybe the obvious kind of hypothesis would be geomagnetism, like the more magnetic perturbations you have, the more irritated people are, or something like that. But maybe something else is involved. I don't know. But that's another interesting thing that I kind of forgot to mention.
Yeah, I suspect it's correct, and I mentioned this before because of the discussion of yin-yang days, yin-yang weeks, yin-yang months, and yin-yang years, and I would say even whole decades. And Chinese astrology is different than Western astrology in that Chinese astrology is time-based more than it is planet-based, and there's this concept of even whole decades of people's lives being affected, and there is a polarity. Takes a part in that the calculations for male and female are opposite, and also for certain people, if they're born with what's called a weak day master, then their calculations will go in a reverse order. So the Chinese were really interested in trying to, obviously they were not rigorous enough, they didn't have enough data to do this, but creating calculations to try and figure out why people would have periodicity in the luck that they had, in terms of how they felt that their life was going. So, they might have like the first 10 years of life was great, and then the next 20 years sucked, and then they would go another few decades and it would be okay, and then at the end of their life it might suck again. So they were really interested in that kind of effect. And I suspect that there is a real effect there that is, I guess, manifested not only in our nerves, which would engage, it would affect how we engage with our environment, whether we're more, again, internally mood speaking, more bearish or bullish, but also that there might be a real effect too. I know that Ben has posted the research, and I looked at it. It looked pretty interesting with the sunspot number correlating to the average lifespan of people. If it's over a certain number, if it's over a certain number, it could drastically affect the average lifespan of a group of people. You wouldn't necessarily tell you about your lifespan, but on the averages. So I suspect that there's a major effect, and I don't know what it is, if it's neutrinos or gamma rays or anything, but I intuitively I think that it is a real phenomenon, and that's a good direction to go in.
Yeah, and there's also this issue that I've only become aware of recently, like literally at this conference, one guy approached me and talked to me about it, is the solar gamma ray emissions. And we've talked about that in the chat a couple of days ago. But, there's a mystery about gamma ray emissions by the sun. In particular, you would expect more gammas to be emitted at the maximum, but that's not the case. It's exactly the opposite. Somehow at solar minimum, there are more gammas, and they're more energetic from the sun. And that's really strange. But those are really high energy gammas. Like they can penetrate the atmosphere easily. They can go to the crust. They can go through your body, cause a lot of secondary processes, potentially at least. So that's also another interesting possible mechanism of influence, let's say.
Very cool. Anyone else have anything? If not, I think it was an awesome meetup today, and we'll meet again on Tuesday, and then again on Sunday. If anyone wants to give any input before we sign off today, definitely invited.
I'd just like to say thanks, Eugene. Amazing presentation. Good correlations, and I love what you're doing. I love where you're going with it.
Yeah, you're welcome. Well, a lot of it stems again from my from what Eidos has made me aware of. So, it's like the very first half of it is really I'm really indulged. So yeah, I wish to say thanks to Eidos again for that. This whole particle physics part.
Well, I really think you did a fabulous job there, and I could clearly see what message you were bringing out there. I find my words are lacking here to express my thoughts. It's the end of my day.
Yeah. Okay. So Since I mentioned you, I also wish to thank Jim, because again the second part was a lot about his work. So yeah.
Yeah,
So
curious, Jim.
so,
Jim, what do you think, man?
Yeah, it's awesome. And I'm just quiet because there's just so many more questions now I have after all this. So, but that's the fun part.